All right, so this is Math 331. We are continuing our work on the egg drop problem. I've looked at some stuff online, and I want to compare the solutions we're looking at with some of the things that are suggested and see what is the best answer we can get. And so we've definitely got some approaches. And we had the stupid, naive approach of moving up one level at a time, which doesn't take into account the fact that you actually have multiple eggs. So clearly this is bad. We had the binary search approach. And the binary search approach initially looks to be better, but still quite bad, because if there are n floors, it could take you n over 2 steps to find the floor where it will first break. But what if you had more and more eggs? What if you had on the order of, say, log base 2 of n eggs, so that you could do the binary search? So my question, the egg drop, if have at least, say, log base 2 of n, maybe plus 1 eggs, is binary best. And again, the question is best with respect to what? And I'll say best with respect to minimizing the worst case scenario. There are lots of things you can do in life. It might seem a little bit bad to be focusing on the worst possible thing that could happen to you. But in a lot of things, that's what you want to minimize. Sometimes you want to maximize the average value. And so in this case, you might want to minimize the average value. So every now and then, oh boy, we're going to be screwed. But most of the time, this will do a better job. And if you can play things multiple times, a lot of times it's a function of how frequently can you do something. There are a lot of games where if you can only play it once, you can't afford to lose $100,000. But if you're playing the game a million times, the odds of losing is so small that you can say, I'm going to win enough that I can take the risk. So we have the binary approach. We had the essentially square root approach. Had the square root of n approach. And then my feeling when I first saw this was that we don't want to drop it at exactly square root of n. Because if that's the case, if we take all these drops until the final one is when we first get one that cracks, and then we have to do all the ones, we're going to have a huge amount of time to do. So we're going to spend a small amount of time in the beginning and a huge amount of time at the end. So the number of steps it takes, the number of drops it takes to find the fraction, the place where it cracks, is going to be highly dependent on where it is. So what this is telling us is we could actually afford to probably drop it a little bit higher in the beginning, because if we needed to do a couple of extra steps in the beginning, not a big deal. It's towards the end, when we've already spent a lot of drops, that we want to have a smaller amount. So my gut feeling was to try like square root of 2n and maybe try to multiplicatively rescale. I looked a little bit online and I found a better way of phrasing it. I'm not sure if the multiplicative way is the right way of doing it, but I liked the way the book was presenting it. What they want to do is they want to make sure that the number of drops it takes to find the key floor is independent of where, which section it's in. So what we're going to do is we're going to do a bunch of drops. Maybe this is drop 1, this is drop 2, this is drop 3, and so on. And of course, the worst case for us is going to be if you do it in a given drop, that was the very first floor where it breaks. And so if that's the case, then you have to go boom, 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 and just march all the way up. And that's going to just take one less than that number. And so in some of the arguments we do, those little bit of one less might actually matter in the end. I hope they don't. But let's see what really happens. So if we had all these drops the same, let's say we do them square root of n. Over here, the number of drops it's going to take to find the bad one is I do one drop in the beginning, then root n minus 1. So this would take us root n drops in the worst case in this range. Okay. In the next range, how many drops would it take us? If the worst egg was in this range, how many drops would it take? Shouldn't be too bad. I'm sorry? So over here, we drop it at 1, it cracks, and then we have to march up one at a time. Now assume we drop it at 1, it doesn't crack. We drop it at the second point and it cracks. And we have, each of these is moving up by root n. Yeah, root n plus 1, right? We just had one more drop, right? This would be root n plus 1. This would be root n plus 2. And then we go all the way to the final drop. I'll put like dots. This is drop root n minus 1. Now let's say we drop it at root n minus 1 and it doesn't crack. Would we really want to drop it at root n? Why not?
Because between the floors root n minus 1 and root n, if the floor that Eddie's cracking is actually between root n minus 1 and root n, which it's very likely it is because there's presumably multiple floors there and only one floor at root n.
Right.
Then if you're dropping it at root n, then you're sort of wasting a drop where you could have just been testing the floor between root n minus 1 and root n.
Yeah, is that, this is floor n over here. And this was floor n minus root n. And so if we drop it here and it doesn't crack, we have root n floors to check. And we have 2 valid eggs. It would almost seem we would want to be moving up maybe like a quarter. Or even do the binary, do halfway. And you eliminate half the things. That at this point, once it's so small, it seems foolish to be dropping it like this. And this is why I'm a little skeptical about some of the posts I've read online, where the strategy doesn't adjust as you go, that it's a fixed strategy. So what we'll see over here in a moment, I think, is a good way around this. But this is why I don't like the idea of always dropping by moving up root n every single time. It's simple, it's easy to do. So now if we do this, this would be, I think, like root n plus maybe root n minus 1. Because at drop 1 it was root n, so we've had an extra root n minus 1 drops. And so the number of drops it takes to find the key floor is going to increase depending on where the bad floor is with this method. And so the idea that I saw online was, well, why don't we adjust how we drop so that we chop this up into a bunch of ranges. And in each range, if the bad floor is located at the worst possible place for us, it'll take the same number of steps. So imagine now, here's 1, here's n. We drop our first one at some point m. How many moves will it take to find the worst floor? Worst case, m. It'll be 1 for here and then m minus 1 to check. So that will take m drops in worst case. And then just because there was yet another email about cheating at Harvard, I will mention I have looked online, and I will be posting the online source that I looked a lot of this stuff up from. So I am not claiming that this part is original. Okay, so this was m drops in this range. So now we want our second range to also require m drops. How much higher should we move up? Certainly less than m. So we've already spent 1 drop. Yeah, we should move up m minus 1. So this should be m plus m minus 1. Because now we'll have m minus 2 numbers to check, and we've already used 2 numbers. So this will now be 2 plus m minus 2 equals m drops in the worst case. And so what we're doing is we're trying to balance things. So we maybe go a little bit higher in the beginning. So m is probably, if you had to guess, how would you compare m to square root of n? A little bit larger. And so now what would the next one be? M plus m minus 1 plus m minus 2. And this would be now 3 plus m minus 3 equals m drops, worst case. And so the best case for us is going to be if n has a certain structure. Right? What kind of number do you want n to be? What kind of... So it turns out that the numbers where this strategy works best, those are a very special type of numbers. Yeah. So the best n are triangular. We want n to be 1 plus 2 plus 3 plus m minus 1 plus m. These are called triangular numbers because you can write them as, 1, 2, 3, 4, and so on. There are a lot of ways to calculate explicit formulas for triangle numbers. What we can, one of my favorites is you take the numbers 1 through m, you write them backwards, you add them up in pairs, you'll get m plus 1, m times, and divide by 2. Very similar to this is I could take this triangle and I could reflect it. And then I would almost double the number. I need to add the diagonal as well. So if I call this number, T4, then if I took T4, added T4, and subtracted the diagonal, which is now double counted, this should be 4 squared. And so then I would get 2T4 is 4 squared minus 4. So T4 plus 4 is 4 plus 1 over 2. And you could do, of course, any number other than 4, but 4 is a great number, right? So there's lots of different ways to prove the triangle number formula, also induction, which we've done early in the semester. So we know that this over here would be n is equal to m plus 1 over 2. So ballpark, m would be approximately what? Square root of 2 square root of n. So the gut feeling of moving up a little bit, like square root of n, is not bad. And then the argument that they were saying is make each range equally bad. So does this sound plausible as the best approach?
Depending on how you define because it's like everything's like kind of okay.
Well, let's say we want to minimize the number of drops in the worst case. That's going to be our goal. So does this seem like this is the best algorithm for minimizing? Because if it is in that first range, we want that number to be as small as possible. And if we start increasing it, then it will be larger than this. So it seems like this is a very good defensible approach. And then what's nice is, as we are getting towards the end, we're doing less and less for our range. So the only question is, as we start getting towards the end, we've already used so many drops in the beginning. Would it be better to do something different when we get down to those last few drops? Well, the whole point here is we're trying to make each range have the same number of drops. So the other thing is, if you ever want to estimate this, another way of saying it is n is approximately m plus 1/2 squared over 2, if you don't want to use the quadratic formula. And this gives a slightly better estimate of m is approximately square root of 2 square root of n minus 1/2. for the most part, it's usually not that important to get that little extra term, but rather than approximating this with m squared, it's a little bit better to use m plus a half, go for the middle. Okay, so this gives us, I think, a pretty good strategy of what to do if we are essentially doing a square root strategy. So how many drops would this take? So this takes, worst case, is approximately square root of 2 square root of n drops. What if we just did our square root strategy? And we talked last time about for exponents, this is the best we could do. If we did an exponent other than a half, we could have too many drops going up to the top, or too many drops as we go up one at a time. So our strategy, so if we do constant size of square root of n, that gave, I think, 2 square roots of n. Or was it 2 square roots of n minus 1? So the worst case is we could have or is it minus 2? Because we will assume that we do the strategy all the way to the beginning, all the way to the end. So we drop root n times to get to the very top floor. And then we would have to do root n minus 1 going upwards. So it would be 2 root n minus 1, which is less than equal to 2 square roots of n. So 2 roots n is going to overestimate it a little bit. What I want to do now is I want to analyze what happens as we get more eggs and see if we can do better than binary search. And this will lead to an interesting calculus problem. So a lot of times in calculus, you get these functions to optimize, these derivatives to take that nobody cares about. I want to have some strange functions arise and talk to you about how you would actually go about solving them. And again, most of you are probably not going to be dropping eggs from buildings. If so, I will visit you when the police come. Just use your call your professor. But the mathematics behind approximating the answer to the calculus problem that's going to come up, that's an idea you could use frequently. So we want to still go if binary is best. So did we do the case of 3 eggs last time? Okay, so let's do 3 eggs first. What if we have 3 eggs? And again, we could try to do a better thing of modifying now the sums of first powers by going, let's just try to do the simple strategy, and let's try to analyze the simple strategy of a constant increment. So what do you think that constant increment should be now that we have 3 eggs? How big should that be? Before it was square root of n. I'm sorry? 2 root n. So still something on the size of square root of n. Are you saying 2 root n? I don't know. Could you say your answer again?
Yeah, well, it was 2 root n because assuming if it breaks on the...
But now we have 3 eggs.
Yeah. The idea being if it broke at 2 root n, then you can just start at root n.
I don't think you want to keep the power of root n. Now that we have 3 eggs, I think you're going to change the power. Do you think you're going to want to do a bigger one in the beginning or a smaller in the beginning than root n? Before we try to figure out, what power we want, let's try to figure out, do we want something bigger or smaller? Yeah, we still have more eggs, right? So because we have more eggs, we can afford to take a bigger drop for the initial one, because if it cracks, well, we don't have to march up one at a time. We can then apply the 2-egg method to that region. So our first step should be bigger. So we know it's got to be bigger than n to the half. So your 2 root n could work, but I think we're going to want to do a power larger. So we want something involving n. What number should appear somewhere in the exponent of this? 3, right? Given that we have 3 eggs, it seems natural to guess that there should be a 3. Do you think 3 should be in the numerator or the denominator? Denominator? Okay, and then what do you think the numerator should be? Really only one possibility since you said it has to be bigger. Has to be 2. Right? If you're going to go with something bigger, and if you're going to go with the 3 coming in the denominator, it's got to be into the 2/3. So, again, we are greatly overkilling this problem. Okay? This is probably more time than you will ever spend analyzing dropping eggs in your life. I really don't care about dropping eggs. But I care about how you approach something like this, how you sniff this out. That's what matters. And then when I look at this, I say, it's got to be n to the 2/3. Now, we could do an n to the delta, and we could do this competing game again. So on this side, I'll just write it as n to the delta. And then the number of drops, this would be what drop? This would be drop n to the 1/3. And this would be drop n to the 1 minus delta. And so the worst case is if I'm over here. So the worst case would be I have n to the 1/3 drops, and then it cracks, and I have to then do that range. And it may be just 1 less. I'm not going to worry about that 1. And now I have something of size n to the 2/3. Well, how do I handle something of size n to the 2/3? From what we've just done before, we can do that in 2 square roots of n to the 2/3. Right? Because it was 2. Oh, sorry. It was 2 times the square root of the size, and the size is going to be n to the 2/3. It may be a little bit better. I might have a savings of 1 or 2. This will be a slight overbound. I don't care. So 1 plus 2 equals 3. So this would be 3 n to the 1/3. And that looks like 113. So I will write it like this. Right? And what's nice is these two n's are going to be of the same power. If I do the other way, worst case. So we have n to the 1 minus delta drops, and then we have 2, and then the size is n to the delta. So it would be the square root of n to the delta. So this would be n to the 1 minus delta plus 2n to the delta over 2. So as n gets very, very large, if delta is less than 2/3, then this is going to be greater than n to the 3rd. If delta is greater than n to the 2/3, this will be greater than n to the 3rd. So we need delta to equal 1/3 or worse than above, or delta equals 1/3 gives the smallest as n goes to infinity. And again, in a lot of problems, you're not going to be able to look at it and immediately see what the right exponent is. For me, this is screaming n to the 2/3. We had n to the 1/2, n to the 2/3. What do you think the next one's going to be? Probably 3/4, right? But if you don't know how to do it, the general parameter, having a free parameter, I love free parameters. And then you just go through the argument, and then you say, what do I need at the end of the day? Now, this is interesting. This method is saying that it's going to take us at most 3 n to the 1/3 drops. It's probably a little bit better with the minus ones, but that's a fine upper bound. Conjecture time. What's the conjecture? So conjecture, k eggs, method gives k n to the 1 over k. Let's prove this, right? So, again, I do not think this is the best method. I really liked the idea of doing a little bit more in the beginning. And this idea of having all of them equally bad, so that no matter where the worst case falls, your method is going to run equally well. Now, of course, the probability that the worst is at the very, very top versus it being in the bottom half is small. So on average, this method is going to do worse. So how many of you are computer science geeks? Taking a lot of CS classes? Okay. Whenever I've talked to a few people about this problem, if there's ever a computer scientist in the room, they immediately start thinking about all the different sorting algorithms. And a lot of these sorting algorithms, they all have the same average runtime in terms of big O, of maybe square root or whatever. Or n log n, I think maybe it's n log n for the sorting algorithms. But in terms of worst case scenarios, there can be wild differences. In terms of the actual constants in the average runtime, there can be massive differences. You know, we're trying to get an order of magnitude. So let's prove it is, you know, k n to the 1 over k with the constant power method. So how should we prove this?
Induction?
Yeah. If at this point in the semester you do not hear it screaming induction at you, you may file a formal complaint with Williams and say that I have not done my job as an instructor. Because at this point, you should be hearing induction, right? When you look at what we did in the third, we reduced it to the earlier case and then fed that in. So this has to be proved by induction. So base case, done. So now inductive step. Assume true for k, do k plus 1. Okay, so how would we do k plus 1? Well, we've got to choose our size. So let's make our steps of size n to the k over k plus 1. And if we go all the way to the top, this would be drop n to the 1 over k
If we were,
plus 1.
this were like a formal write-up,
Yes?
would we have to, how would we explain why we picked k over k plus 1? Because it seems like it wasn't extremely rigorous how we, I mean, yeah.
So divine inspiration always works. So when you're doing an argument like this, if you happen to just choose the right thing, you're fine. And so in the proof of the inductive step, we need to make a choice here. You're absolutely correct. We could actually do the free parameter delta again. And so if we don't know that it's k over k plus 1, we could do the parameter delta. The other thing is, the more points you get, the more data you get, the better chance you have of sniffing out the pattern. So we could go back over here. We've just done the case of 3 drops. We could do the case of 4 drops and see that we get 3/4. And then that would suggest, and the reason that you should not be surprised here is we're going to be taking a square root of this, so the 2 will vanish. For the next one, when we have 4 eggs and we do a drop, once we have a crack, we'll take a cube root. So at 3/4, the 3 will vanish. So it's highly suggestive that it should be k over k plus 1, but if you don't see it, you do the free delta argument. And then at the end of the day, you want the powers of these two to be the same. Because if the powers are not the same, let's say this power is higher than this power. Well, if this power is higher, then I can increase delta and shrink this and grow that. So the way you equalize these two terms is you make the powers the same. And that is an extremely powerful technique in a lot of number theory problems, is you have these two competing terms, and you say, okay, let's make them equally bad. I don't want to choose who I hate the most. So it's natural to guess k over k plus 1, but if you don't see that, you are, of course, able to just go through the delta argument. So now the worst case is going to be n to the 1 over k plus 1 steps. And now you're beginning to see maybe we should have done k minus 1, because then we would have cleaner denominators. Plus, now we have k eggs and a range, at most of n to the k over k plus 1. Maybe it's 1 less. But we can overestimate a little bit further out. And so now, from induction, it's going to be k times the kth root of this. And the kth root of this is going to be n to the 1 over k plus 1. And so when you sum them, you'll get k plus 1 n to the 1 over k plus 1, as claimed. So this method shows that our conjecture is correct. This does not show that this is the best. It just shows that if you have k eggs, you can do it in k n to the 1 over k. So we are comfortable about this? Yes?
Just reviewing the 3 egg.
Yes.
Case again. I just don't really see how we're actually using 3 eggs, because it seems like we're just dropping at to the 2/3 intervals. But how is that incorporating 3 eggs?
So let's say we drop our first egg, and the first time it breaks is at the very top. Now we have an interval of size n to the 2/3 and 2 eggs.
Okay.
And now we feed in, and that's why I'm saying over here size n to the 2/3. So we have 1 fewer eggs. I could say 2 eggs okay, and then over here we'll just have 1 egg. Okay, so we all happy? Conjecture is true? Okay. So now we've shown the following. If have k eggs, at most, k n to the 1 over k drops, in worst case. What question now is screaming at you? What question should you be asking? So there's average case. We're not going to deal with average case. That's unfortunately beyond the realm of what we can do in this semester.
Can we generalize the previous method?
So one possibility is generalizing the previous method where we did, m minus 1, m minus 2, and see how much that improves things. We could absolutely do that. But I'm saying once you have this line, this should be a question you should be asking. So if you have k eggs, it's going to take your k n to the 1 over k. Any thoughts as to what question you might want to ask here?
Does it make sense?
Well, okay, so the answer does seem to make sense as, does the answer make sense? What should be happening is you have more and more eggs. It should be decreasing. So does k n to the 1 over k decrease? Will this decrease for all values of k? What happens as k goes off to infinity? What does n to the 1 over k go to? 1. So clearly, if k gets really, really large, this is going to get worse. Can you imagine needing n squared eggs when you only have n floors? Or n to the 5th eggs? Or e to the n eggs? So clearly, we do not want to use this with more than n eggs. So, is this decreasing? Is this decreasing for 1 less than equal to k less than equal to n? Do you think we're going to need to go all the way up to n eggs? What's the smallest n to the 1 over k could be? I'm sorry?
N over 2.
No. As k goes to infinity, what does n to the 1 over k go to? 1. N to the 1 over k is at least 1. Let's make a table. K n to the 1 over k. When k equals 1, well, we get n. Makes sense. Can't do better than that. When k equals 2, we get 2n to the 1 half. When k equals 3, we get 3n to the 1 third. When k equals 4, we get 4n to the 1 fourth. 4 is larger than 3. That makes me a little bit scared. But I would much rather have for large n an n to the 1 quarter over an n to the 1 third. This is much smaller. As k keeps getting larger and larger and larger, will these numbers eventually flip? Yeah. Once k becomes a small power of n, this is going to start to get worse. If k was like square root of n, then we'd have square root of n. Even if that's just 1, that will definitely be worse than 4n to the 1 fourth. It's not going to keep going down forever. So what's the question you should ask? Yeah. What is the best k? Now, when I say what is the best k, you're thinking that you have to find the best integer value of k. We will allow ourselves to have a continuum of eggs. This is a calculus problem now, right? So this is a really long motivation to try to get to a calculus problem. So let's consider f of x is x n to the 1 over x. I want to find the best value. I want to find where this is smallest. Do we have to worry about finding, so how would you find where this is smallest? What would you do? Derivative. And what else, please? No, no, come on. I hate doing this, but please tell me where I'm moving the fastest, okay? Okay, what did you forget to check? Endpoints, yes. Okay. We definitely need more shock-absorbent blackboards in the new Bronfman. It hurts. Okay? Remember that. I don't want to do this again. Always check endpoints. Now, for this one, you know clearly, well, when k is 1, it's going to be n. And as k goes off to infinity, it's going to go off to infinity. So you don't have to worry about endpoints. And so, in fact, it's enough to look at the interval from 1 to n. And now we have a continuous function on a closed bounded interval. Real analysis tells us there's going to be a maximum and a minimum. So when we do our calculus, there will be a unique minimum. So we'll be fine. Okay. So now find x, the critical point, such that f prime of x equals 0. And I'm going to rewrite f of x as x e to the log of n over x. Just so I can differentiate. And now, f prime of x, all right, well, derivative of x, that's not a problem. That's just going to be e to the log of n over x plus x. Now I have to take the derivative of e to the crap. So I get e to the crap back, log of n over x. And now I take the derivative of the exponent. So that's going to become a negative log of n over x squared. Well, I can factor out the e to the log of n over x, because that is always non-zero. And then I will have a 1 minus log of n over x, because one of the x's will cancel. Therefore, critical point is when x is the log of n. How does this relate to the binary method? More eggs or less eggs than the binary method? So let's compute a binary. So here, so we'll say constant power, we need log n eggs. In binary, how many eggs do we need? So how many eggs do you need when you're doing the binary? You need cut in half again, cut in half again. How many eggs? Log 2 of n. Which is more, log of n or log of n base 2?
N base 2.
So how many people say the log of n base 2 is larger? Right? Because here I need to raise 2 to a power to get n. Here I need to raise e to a power. So I'm using fewer eggs than binary. So here's the big question. Which is better? So what binary, what's the worst case?
I think you flipped the gradient, like it should be.
Sorry, I did flip the gradient, yes. So now we just need to do worst case. So the worst case for the binary is how many steps? Yeah, just log 2 of n. Right? Because we have so many eggs, we just get all the different digits. The first egg gets us the first digit, is it a 1 or 0? The second egg gets us the next digit, is it a 1 or 0? This is not like the Euclidean algorithm or something where we now have to do like a double. It's just the log of n. And then the constant power, we now have k n to the 1 over k. So we're going to have the log of n times n to the 1 over log of n. Anybody know what n to the 1 over log of n is? Yeah, because you write n as e to the log n. So this is just going to be e log of n. Oh, so now which is larger, the log of 2 or the log of n? The log of 2 is larger, but we have this factor of e. So which do you think is better? We're down to log laws, right? It's been a long, right? It's been a long time since we've done stuff like this. Change of basis, one of my favorite log laws, the most forgotten of the log laws. The reason change of basis is so useful is in the days before computers, people had to have tables. And if you have the change of basis formula, if you know logs in one base, you know logs in another base. So if I want to calculate the log of x base c, this is the log of x base b over the log of c base b. Did I get it correctly? Okay, so now the log of 2 base n would be the log of n base c over the log of 2 base e. And I want to compare this to e to the log of n. So it's now 1 over log 2 versus e. Well, the log 2 is less than 1. Anybody know approximately what the log of 2 is? It's a good number to know. Yeah, very good. It's about 0.69. I normally do about 0.7, but 0.69 is actually better. So this is about 7/10. This would be about 10/7. Clearly less than 2. And so we can put it like this. So This is not a proof that binary is best when you have a huge number of eggs. Maybe the approach where we had no longer, constant intervals, when we tried to equalize how bad things were. As a nice example, you can actually look at the plot of the function, x(n to the 1 over x. It's, kind of interesting to see. What I want to end with, I've got about 2 minutes left. I want to end with a quick idea of how you might try to figure out what's going on. And so this is the divine inspiration. So I've got f of x is x n to the 1 over x, which is x e to the log of n over x. And what you might want to do is you might want to just try guessing various things for x. What you could do, and then I know they have differential equations going on here in about 2 hours, a little bit over an hour, I guess. What do you think would be a good starting point for x? Just looking at this expression. When you look at this, you see a log of n over x. So maybe try x equals g of n log n. Because if you try that, this will then give you g of n log n, and then you'll have e to the log of n g of n. So in fact, what maybe we might even want to do is try x as the log of n over g of n, maybe put g of n downstairs. And then we would get log of n over g of n e to the g of n. Oh, this shows me that if g of n is growing, this is going to be going much faster than this. So I don't want g of n to be growing. So it tells me, if I take g of n to be constant, I now maybe want to optimize, 1 over c e to the c something. That's very similar to what we were just doing over here. But it gives you a rough idea to sniff out that a log of n is actually reasonable. And it's nice to be able to just look at stuff like this and get a feel for what the answer is. Okay, so this is a good place to stop for today. Today's Friday. So on Monday, we will go and we will talk about the domino problem. And what I like is the domino problem is a phenomenal example of where your intuition is bad. That the harmonic stacking, and we'll show why the harmonic stacking works, it's not even close to what the best is. And again, this is a luxury at Williams to have a class like this, where we don't have to learn specific material. The goal is to have, at one point in your life, you to look at things differently.